In this lesson, we're going to learn a bit more about the APIs that pointer tensors offer and the full range of functionality they give us when controlling pointers to tensors on other machines. Now, the first thing we'd like to do is initialize some data to play with. So let's say x equals a torch tensor, and we'll send this to Bob, and y equals another torch tensor, perhaps a tensor of ones, and we'll send this also to Bob. Now, of course, if we were to send one to Bob and another one to Alice, then we couldn't do any functions that involved both tensors because, as you'd imagine, they wouldn't be on the same machine. So as you can see here, we have tensor x, which is a pointer tensor, where the pointer is located on the worker called me, which is the one that's, as mentioned previously, initialized inside the hook, and it has an ID of this 873 big number. But it's pointing to a tensor on Bob with an ID that starts with 99233, and y is quite similar. And the nice thing about these pointer tensors is that we can just pretend that they're normal tensors. So if we go z equals x plus y, we are returned a pointer to the output of x plus y executed on Bob's machine. And we can go z equals z.get. And as you can see, the output is correct. So it took this 1 to a 5 and added 1 to each of the individual values. Now, if you prefer to use some of Torch's functions instead of using methods, you can also go z equals th.add. We can pass in x and y, and this generates a pointer to the output again. And of course, we can go z equals z.get and look at z, and we get the same result. However, Torch is used for more than just simple operations, and it actually has some more advanced protocols. So if you consider, say, backpropagation. So if we were to instead create a couple of tensors which had variables and send those to Bob, we can even use this more advanced functionality. So let's say x equals th tensor again. Actually, let's just copy these guys from up here. But instead, we're going to say requires rad equals true, floating point numbers. So now if we go z equals x plus y, we'll sum that to a single number. And then z backwards, so we'll call backpropagation. What this would do normally is it would create gradients on x and y. And so if we actually call x back, we have x itself, and we have x dot grad, which is a tensor of ones, just as it should be. So as you can see, the full API of PyTorch is at our disposal. And as much as possible, the creators of PySyft have tried to make it feel like you're using normal PyTorch as close as possible to the original API. So this leads us to the next project. What I'd like for you to do in this project is leverage this API to train a simple linear model. So you're going to use sort of the backward function, you're going to use variables, and you can even use optimizers or things from inin.modules, so like inin.linear, for example. So you might be familiar with this module, right? So, and just learn a simple linear model with one core constraint. I want the data and the model to be located on Bob's machine. So take a stab at this project, and in the next video, I'll show you how I would do this with PySyft.